So for our presentation, we're just going to do a brief introduction of just what the experiment actually was, the relevant history, like why we're doing the experiment, because there actually is some, which is kind of cool. The overall reaction, we have some pictures of the overall experiment, so you can see kind of what to do as we go. We're going to show you how to analyze the data, sort of, safety hazards, and some ways to improve it. Okay, so we're going to be using the gas chromatography, mass spectrometry, to analyze the degradation of PCE and TCE. I will get into further detail about what those are, but they're organic complexes with, or organic molecules with chlorine, chlorine bonds. The GCE is used to separate the individual components within the machine or the instrument itself, and the mass spectrometry is used to separate them and identify which product is leaving the instrument at different times. The area of the peak, when you get the peak from the integration, shows you the relative concentration of the component that you try to separate. There's an internal standard that we use. The internal standard in this experiment is toluene, which when you compare the relative ratios from one to another, you can kind of see the relative concentration from one another. Okay, PCE and TCE, this is perchloroethylene and trichloroethylene. It's utilized industrially and commercially. It's very often used in dry cleaning solvents, which is not very good because it's not really a good way to get rid of them. It has caused a lot of contamination of water and soil due to improper disposal. There's actually a little city in Taiwan that had a huge company that produced these, and they got rid of them really poorly, so they ended up like poisoning the entire village. And that's not good, considering it's a group 2A carcinogen, which is probably carcinogenic to humans. But in that little Taiwan city, there was over 1,000 cancer cases, which is ridiculous. So it has to be regulated, and it's limited to 5 micrograms per liter. Why is it important? Because it's non-polar and it accumulates very easily in the body, especially if you have a large consumption. It's very strong, and the covalent bonds are very, very difficult to break. It has been noted that cobalt, however, is very good if you try to break it down, and a very natural cobalt-containing biomolecule is vitamin B12 or whatever. And in this experiment, we're going to be using TCCP cobalt, and we're going to try to just measure how quickly and how effectively it degrades the chlorine.
So just to clarify, these are the structures of the chlorinated ethylenes that we'll be studying. So PCE is the perchloroethylene, and then the TCE is the trichloroethylene. So from these two structures, you can see that TCE is actually a dechlorination product of PCE. This is kind of reiterated in the overall reaction scheme here. So you can see that PCE is being reduced to TCE. The cobalt catalyst that we're using is this transition metal complex, TCPB cobalt, which is it's a synthetic molecule that essentially mimics and is actually better than vitamin B12 in dechlorinating ethylenes. It's the catalyst of the reaction, and it's losing 2 electrons here. So one of the electrons is used to reduce a chlorine from the PCE to a chlorine ion. The other one is reducing a proton to form a carbon-hydrogen bond. The reaction is second order, and the rate equation is shown here. We're able to simplify it to the bottom rate equation. Oh, that's why it's not natural. Oh, perfect. Okay, so this is our rate equation, and we're able to simplify it to this one right here, because essentially the concentration of our catalyst is constant, right? Because we're regenerating it. So the rate only depends on the concentration of the PCE.
So I'm going to talk a bit about the instrument that we're using. This is the inside of the GCMS. So we have both, basically the GCMS uses both methods of gas chromatography and mass spectrometry to identify the different substances in the sample. And this is a little clearer picture, it's a drawing. Basically the gas chromatographer has a fertility column, which is that right there. And it depends on the column's dimensions, so the length, diameter, thickness, and phase properties. And the difference in the chemical properties between the molecules in the mixture will separate the molecules as the sample travels through the length of the column. The The molecules stay in the column and then elute at different times. So different molecules enter the mass spectrometer at different times. There's the mass spectrometer. And the mass spectrometer captures, ionizes, accelerates, deflects, and detects the ionized molecules separately by breaking each molecule into ionized fragments and deflecting these fragments using their mass charge ratios. Using both the gas chromatographer and mass spectrometer together allows for a much more accurate substance identification, since it's very unlikely that two different molecules will behave in the same way in both the gas chromatographer and mass spectrometer. Okay, so I'm just going to go through the procedure a bit. We took some photos. And basically, we start off by using a micropipette, and we have vials which will later be sealed with a clamp, so they'll be airtight. We use a micropipette to inject buffer into each vial. Each vial also receives 250 microliters of PCB, and those are the vials, and that's the cap. The titanium-3 citrate will be injected into 2 of the 3 bottles, and this part must be done carefully. So we go into further detail for that. That's the titanium citrate, the blue stuff. We want to keep it under nitrogen. We want it in its reduced form, and if oxygen gets in there, oxygen's an oxidizing agent, and we don't want it to oxidize the titanium. So, before inserting the actual tube of nitrogen gas into the lid over here of the titanium citrate bottle, we insert a tube so the air can escape, and that's that yellow thing here. And we just poke it through the bottle. Then we turn on the nitrogen tank. And then we insert the tube of nitrogen gas just next to the tube where the air escapes. Just through the lid, it pokes right through. Okay, and then in order to get our sample of the titanium citrate, we carefully lift the lid off of the bottle, just like a very small amount so we can get the needle in, because we don't want the oxygen to get in. And we use the syringe to suck up 250 microliters of titanium-3 citrate. And then we put the lid back on and just let the bottle sit for a few minutes with the nitrogen flowing through. So if any oxygen did get in, it helps it to get out. And we also found that using a clamp for this part with the bottle of the titanium citrate, it was a lot easier than trying to hold on to it. Okay, and also be sure you label your vials so you don't get them mixed up. There will be 3 of them. Okay. And next part is we use a clamping tool. This part should actually be done before we actually suck up the titanium-3 citrate, so the vial's all ready for us to inject it into the airtight bottle. The clamp is really easy to use. It fits right over top of the lid, and you just put it on and squeeze it together, and it clamps it onto the vial, and it's airtight after that. Okay, so also before injecting the titanium-3 citrate, we set up the nitrogen gas tubes just as they were with the actual titanium citrate. So we first insert the tube for the air to escape, and then we insert the tube with the nitrogen gas. And this part we also found that it's easier because we can't really clamp the vials because they're delicate and they're really small. So maybe just have one lab partner hold on to the bottles while the other one inserts everything into the lid. Okay, and yep, this is just another picture of one partner holding the bottom and the other one inserting the nitrogen gas tube. And so then we inject the titanium citrate into the vial just by poking it through the lid. It's dark blue in color, so you can't really see it in this picture. Okay. And then later in the experiment, we'll need 125 microliters of TCPP cobalt, and that will be be injected into only one of the tubes, the third one. And so we just will be directly poking it through the lid of the bottle, just like we did with the titanium citrate. And we want to place all 3 of these vials into a stand bath at 35 degrees. And just make sure the liquid is all covered by the sand. Just we want to keep the temperature constant.
Okay, then on the computer, you click the computer icon.
And one thing I'd like to stress is that you're going to be taking headspace out of the vial. So the reason we put it into the 40-degree bath, you're going to get an equilibrium between gas phase and liquid phase. So that takes about 15 minutes for that to equilibrate. And don't dip your needle too far into the liquid because it will ruin the machine. You just want some gas. The layer, just put the needle in just a little bit into the vial, not all the way. If you see any liquid when you're playing around with the injection. I don't know if you're going to go through this, but sorry.
Okay, so you click on the computer icon to open the program. And you click on acquisition to actually run it. Then you can click on that little vial to enter your sample name. Make sure you enter your name, the sample name, and the time for all the samples. And this is how the needle looks like. And make sure you place it in a holder every time you use it. And so for injecting it into the vials, make sure you hold the needle from the bottom so that you don't break it. And inject it into the headspace air and take out just the air and not touch the liquid. And before doing it, take it a few more times before actually taking 10 microliter out of it. And then quickly inject it into the machine. Okay, to stop it, you have to actually press the reset button, and then you can view the chromatograms of each the sample of your depth.
So it's set for, I think it's set for 10 minutes, but these samples go through, by 3 minutes the chromatography is over, so you don't have to wait for 10 minutes, you can just reset and then.
Yeah, after 3 minutes, like the peaks set up, so there are no more peaks after it. And these are the different peaks of the components present in the sample. So you can integrate it by clicking on the integrate button there. And you can actually get the areas of all the peaks. And in the end, make sure you press the stop button.
So that was a good overview of how the instruments work and the actual procedure. Our data analysis is going to consist of 2 parts. The first of which is going to be estimating the rate constant. So as I mentioned before with the rate equation, the integrated rate law for a first order reaction is shown right here. So we're all familiar with this one. So this concentration here is the concentration of PCE at a given time of sampling, and this one here is the original concentration. So if we go back 3 slides, we can see this is what our output is going to look like. On the top here is our gas chromatography output. Here's our mass spectrometry, which I'll get to in a moment. But if we consider this, the detector is actually counting how much material is within the sample at a given time. So our horizontal axis here is time, and this is actually the machine's counting how much material is present. So the highlighted red area, these are the areas under the peak, are directly proportional to the concentration of a component within the mixture at a given time of sampling. So this is how we can make our integrated rate law usable, or put it into a usable form, because we have the areas of peaks. And like Jeff was mentioning earlier, we're doing it against the standard. Our standard is toluene, because we want to normalize our data. So that's why we're dividing the area under the peak of the PCE and the area of the toluene. So from this, we're going to be able to isolate for the rate. So that's nice and useful. The second part of our data analysis is going to consist of actually reading our mass spectrum. A mass spectrum is basically a plot of the mass to charge ratio. I'll zoom in on this image in a moment. But you see the horizontal axis here is the mass to charge ratio of many components. And here is the percent abundance of ions. So if we look at this example, this is actually the mass spectrum So if we kind of consider the important parts of this graph here, we're considering the molecular ion peak, which is the first peak that we're going to kind of concentrate on. It's also considered the M+ peak. So this is going to be correlated to the actual mass of our starting material, which in this case is going to be PCE. In essence, the mass of PCE is roughly 164 grams per mole. We're going to see a peak kind of appear right here. Okay, so that is our molecular ion peak. All of these lines, these are all degradation products or fragmentation lines. So they're all fragmentation products from the reaction. There's also some isotope lines that we won't really have to worry about. That's getting a little hairy. But if we consider a degradation product, we know that TCE is a degradation product of PCE. TCE has a rough molecular weight of 130, and we'll see that line right here. Okay? So this is how we're going to be able to determine what degradation products we have throughout our reaction, and that's essentially what we're doing for our data analysis.
All right, safety hazards. We've all been in chemistry labs, so just take natural precautions, I guess, especially with everything. Don't drink it. We really want to stress the most important thing is handle the needles with care. We don't want to get pricked, obviously, and we only have 4 of them left for this entire lab session, so we don't want to break them, which is very easy to do when you're kind of in a rush. So just be very careful in handling those. Here are some potential improvements.
Okay, basically the chemicals are really volatile, so use a needle that's better insulated. Your body heat when you're touching the needle, if you hold on to it for too long, it might affect the chemicals in there and warm them up. We don't want that, so maybe a better insulated needle. Also, we found that 2 people performing the injections made things a lot easier because the one person could hold down the vial, whereas the other one uses the needle, and it keeps everything a lot steadier. And also because the person injecting really should always have their hand, like 2 fingers on the needle itself so it doesn't bend or break. It's easier when 2 people do this together. Also ensure time begins at the time of injection into the GCMS. So basically when one person's injecting into the actual machine, the other person can click the button on the computer to get it started. We also found, like I mentioned before, using a clamp when injecting the chemicals with nitrogen. It just made things a lot easier, we found, a lot more steady. And also auto sampler, it reduces human error and increases accuracy. And what that does is it actually injects, it's a machine that injects the sample itself. So we wouldn't even have to touch it. So we wouldn't have to worry about things like body heat or going too fast or too slow. Auto sampler would do it all. So that would just make things a little bit easier. That's it.
Do you have any questions? Or
That was excellent. I just want to make, so the comment about body heat, that's why we have the internal standard. So, and from person to person, everybody has a slightly different injection. So having that constant internal standard of value, we adjust for that. And auto sampler, we did everything automatically that you want to learn, and plus it's really expensive. So wait till you have your own rich lab. What else? Oh, so those hairy bits about the titanium. Oh yeah, you didn't mention why the titanium is used. So you have cobalt, the cobalt catalyst, and then you have some titanium in there. What's the titanium?
With titanium, it needs to be in its reduced form so it can, needs to be reduced in order to break the chlorine bond.
No, so the cobalt is the catalyst. The cobalt complex is the catalyst.
Okay.
So that cobalt cap goes from cobalt 1 to cobalt 2, so it has to be re-reduced. And titanium is the reducing agent. So that's why we want that titanium in its reduced form, and it's in excess. And so it just sits there. As long as there's titanium 2 around, that reaction keeps going until all the chlorine is used up. Okay, Excellent. Any other questions, comments?